We use data compression every time we use our computer, but we hardly even notice that it's there. But it makes everything faster and more efficient. So, what is data compression? Data compression reduces a file size with little or no loss in information. There are various methods of compression, meaning different file types undergo different kinds of compression. In this video, we are going to talk about lossless and lossy compression, which are the two main types of data compression. A basic visual representation of compression is having an uncompressed file or file that we want to compress, and then we use the necessary compression algorithm for the file, and it out comes a smaller file that may or may not have lost information. We can calculate how much is compressed by using the formula of the compression ratio, which is uncompressed file size over compressed file size. In order to use this formula, you must first understand bits. Bits are what computers understand, much like how switching of strings of letters can form words with different meanings. Computers use strings of digits to form its letters. Here we have 8 digits, with each digit corresponding to one bit, and each bit corresponds to a value. In this example, we have 8 bits, or what we call a byte. Whenever a bit is turned to a 1, the value changes, which is indicated by the number in the green box. Each time we increment a 1 alongside the other ones, the value is added by the bit's corresponding value. We don't always have to progressively increment the bits. Bits can be turned and remain to a 0, while other bits can be turned to a 1. If we turn everything to a 1, then we get a byte's maximum value, which is 255. With this information, we can understand how a computer forms letters, or more accurately, characters. We use the ASCII or American Standard Code for information, and it shows each letter has a specific code represented by bytes. We will only focus on the decimal and the binary value of each ASCII character. Here we have a byte which have a value of 72, which corresponds to the letter H. And here we can see that it does correspond to the letter H. And here we have another letter which has a value of 105 and an ASCII character of the letter I. And indeed, the decimal and binary value corresponds to the ASCII character I. And then we have a value of 33, which corresponds to an exclamation mark. And so, by stringing these bits together, we can form the word hi, which the computer can understand. Now we can proceed with data compression. Lossless compression, from the name itself, loses no information, meaning we can revert the compressed file back to the original file. But this type of compression is mostly used in text files. It is used for files in fields that involve finances and human lives, because a compression mistake can mislead a banker or a doctor from the actual information. Huffman algorithm is commonly used in lossless compression and maps characters to shorter codes. In order to use the Huffman algorithm, we use the frequency of the characters or letters in a word. And here is the process of the Huffman algorithm. First, we construct a leaf node for each letter with its corresponding frequency. Here we make a table that shows the letters with its frequency. From here, we can easily divide them into nodes, again the character with its frequency. We then sort the nodes in increasing order. Using the sorted nodes, we pair the nodes and their frequency. As we pair them, we take the sum of the character's frequency and store them into a parent node. We again pair the combined nodes, which results in these values 4 and 6. We continue in combining the nodes until we get a single node at the top. We can label the arrows or lines that connects the nodes with zeros and ones. This can help us in mapping the characters into code. For the character C, we start from the top to the node that contains the letter C. So 0, 0, and then 0. And for the rest of the characters, here are the codes. For the letter O, we get 1, and then 0, and then another 0. For the character S, we see that it only has two values, 1 and then 1. Here are the uncompressed binary codes for each character and the Huffman algorithm codes of each character. The word compressor contains this number of bits using the standard or ASCII system. And you can clearly see, using the code we got, we use a smaller number of bits for the same word. We can compare the uncompressed size to the compressed size. Here we have a total of 80 bits or 10 bytes, and here we have 28 bits or 3.5 bytes. For the compression ratio, we divide the uncompressed data size to the compressed data size, and we get 2.8571. For the space saved, we use the formula 1 minus compressed data size over uncompressed data size times 100. So we have a space saved of 65% or 58 bits. With lossy compression, we can afford some loss in information, so the compressed file cannot be fully reconstructed back to the original file. This is because human limitations are factored in, meaning the limitations of the eyesight and the hearing. With photos and audio files, we have file types such as JPEG and M4ACE. However, we will only focus on the JPEG. To compress an uncompressed image file, let's say from a PNG to a JPEG, we use discrete cosine transform. Discrete cosine transform represents image data as a sum of cosine functions, and the less important frequencies can be discarded. We use this image from a game called Cyberpunk 2077, and to compress this image, we can divide it into smaller squares that represent the most dominant color in each square. However, these squares are much too big for the algorithm to work. Using a block in the image, we can imagine to divide it again, this time with much smaller boxes we call pixels. Each pixel is represented by RGB values, which are not the only component, but for the purposes today, we will only focus on the RGB values. Each RGB value ranges from 0 to 255. We get this value by averaging this pixel's RGB value. So for the value of red plus the value of green and the value of blue divided by 3, we get this number. And here we do the same. And here again, and these first 8 values correspond to the first row of these colors. And these next 8 values correspond to the second row of these selected colors. We can represent these values by plotting it in a Cartesian plane. I use 10 for the value between x for the purposes of showing a more spaced graph. After plotting the points, we can get the average of the values, which is 191. We can now proceed with the cosine function. Recall that this is what the basic cosine function looks like. After we construct our cosine wave, we can then raise it to where our values lie. And we do that by adding the average to the vertical shift of our cosine function. We can manipulate our cosine function further to match our points. And here, since the average difference of our points is 3, we can add 3 to the amplitude. Recall that the amplitude is the distance between the highest point and the lowest point of the wave, or we increase the height of the wave. We do this to match the values of our points closer. We can add a period of 1 over 10, and recall that a period is the length of one cycle of a wave. And by adding the period, we can see that our cosine function is so close that we can actually disregard the inaccuracies here and still see the same image. So we can now replace these values with just one function of a cosine. And for the second value, we do the same thing. We just keep manipulating our cosine values until we match our pixel values. This is again our graph with the white line representing the pixel's accurate values. In simpler terms, this graph shows from like saying to a computer, for this pixel, use this value, for the next pixel, use this value, for the next pixel, use this value, to for the next 8 pixels, follow this cosine function thread and use its values. So again, we go from this many numbers to just two functions.